Thanks. All right.
That's just somebody said that. Actually, my phone has channels, so pardon me for the color.
So this is the system, and the goal is to find the center of mass of the system, or the distance from the origin, which is the center of the ball, to the center of mass. So I'm going to draw this as a point particle system because it'll be easier to find the center of mass that way. So, oh, this sucks. I'll call this M2, M1, and this is M3. So this would have been the sphere, but since everything is constant density, or uniform density, I'm just going to draw them as points. So then this would be the bar. So you have some distance here that's d over 2. This distance would be L1 over 2. This distance is also L1 over 2 because the center of mass of the bar is just going to be in the center. And then this distance is L2 over 2. And then let's call this point O. That's just the coordinate system. And then you obviously have like the masses. M1 is 6 kilograms, M2 is 4 kilograms, M3 is 10 kilograms. So the formula for the center of mass is the vector from the origin to the center of mass is sum of masses times their corresponding vectors over the total mass. And so if we just analyze this system mass by mass, let's look at M1 first. So M1 times the vector, and then from O to M is just in the negative x direction, d over 2 and L1 over 2. So negative d over 2 plus L1 over 2. And then nothing in the y direction. And then for the second mass, M2, it's going to be negative d over 2 and then all of L1 in the x direction. So negative d over 2 plus L1. Nothing in the, in the y direction, it's negative L over 2. And then for M3, since this is like where you're taking the center of mass with respect to, it's just 0 because the vector from O to O is 0, so plus 0. And then if you plug everything in, the values of L and D are given, M1, M2, M3. If you plug all of that in, I don't want to show it. And also this is over M1 plus M2 plus M3 by that formula. You plug all of that in and you'll get the vector negative 2.1, negative 0.18 meters. So that means that the center mass of this system is like somewhere, I don't know, somewhere like here-ish. But we want the magnitude of this per the question. So if you just take the magnitude, square both of them, square root, and you get 2.1077 meters. The magnitude of ROC.
Okay, sure. 1.3. Is this the one you used? Yeah. Okay. Yeah, that's the one. So that's our system, which we just have the cylinder and a hemisphere on top, okay, with the radius R and height of the cylinder L, and L they gave us to be 1.8 R, and R is equal to 1.3. I believe this is in meters. So I denoted the center of mass with, or sorry, the z component. So you would define the z component of the location of the mass center of the body. So that center of mass is going to be all the positions of the center of mass. Like, so basically, we have two objects here. So each of these center of mass, and then times their volumes all over the total volume. So first, let's start with the cylinder. So we know that that position is going to be at L over 2, because this is L. So we have L over 2. And then for Z2, it's going to be somewhere up here. But for a hemisphere, the center of mass is at the height 3/8 r, r being the radius. So we can say L plus that 3/8 r. L plus 3/8 r. And then for the volume, we know the volume of the cylinder is pi r squared times the height, which is L. So pi r squared L. V2, for a full sphere, it would be 4/3 pi r cubed, but we're working with the hemisphere, so we divide that by 2. So 2/3 pi r cubed. And I will substitute L equals 1.8 r for all of these. So we got 0.9 r, 2.175 r. This will be 1.8 pi r squared, or sorry, pi r cubed because of this r. And then over here we have 0.67 pi r cubed. So now we have to multiply each of these in sets, divide by the total volume. So z bar equals, so we have the sum and I just evaluated this at r equals 1.3 meters, so I'll just write that here. And when you plug this in, you get 1.6180 meters. Yeah. Yeah. Yeah, sorry, it's very hard. It took me 2 hours to finish this. Yeah. All right, so because this is a very hard problem, I won't go over too much detail. We want possible units of linear momentum. So linear momentum is equal to d dt of mass times the r vector. So using the product rule, we get m dot r plus m v vector. Let's look at the units of all these. So m, we can get kilograms, pounds, slugs, pound mass to be specific. M dot, we can get all that over second, pound mass per hour, different units of time essentially, something like that. We have R, which is in meters, feet, inches, whatever, and then V is going to be the same thing except over seconds, feet per second, inches per hour type thing. So we have all these units. If we combine them together, they end up with the same units, which can get you to kilogram, meter per second, slug, feet per second, all that stuff. And then we have newtons. The base unit of newtons is comprised of multiple units, it breaks down into kilogram meters per second squared. Now, if you take this and then you plug it into that, you basically get this is equal to newtons times 1 second. So all three of those unit works. Joules does not work because joules is newtons times meters, and that's a completely different unit. Okay, so that's 2.1. I also did 2.2.
Newton second is a very important unit because there's a correlation between impulse and momentum.
Yes.
And correlation, you typically use impulse in Newton second and the momentum in kilogram meter per second.
Yeah. Okay, so 2.2, we want the magnitude of the linear momentum, so I'll just use the same formula. L is equal to, I'll put a vector. L is equal to I d dt of m r, and then we'll call this A because we want the position vector. Since the mass is not moving, we can just simplify this into m with inertial frame of reference and then v a. Let's just call an inertial frame of reference I x I hat y j hat. We'll call this I, so we're going with that. And then we basically, so it's either this way or it's equal to, and we want the magnitude, so we put, I don't know what these actually called, magnitude braces? Sure. We could do that. So both of these are equivalent. It doesn't matter which way you did it. I did it this way because it was easier. We have 6 kilograms times the magnitude of 5 meters per second in the I hat plus 5 meters per second in the j hat. Do the maths and you get 42.4264 kilogram meters per second. And as we saw in the previous question, the units line up.
Like the due diligence in terms of being so specific about all the rotations really helps more complex problems.
So for this one, we have a 2D momentum. Basically, a particle A has a certain momentum, particle B has a certain momentum, and we have to calculate the total linear momentum in the x direction. So let me draw the system here. And I guess if you want to set up the coordinate system, we have, we just have the x, I hat, and y, j hat. Yep. Okay, so we have the momentum. So first, let's let's draw out the diagram. So we have A moving at VA, and then we have B here. Okay, so VA, they gave us as 9 I hat plus 9 j hat meters per second. And mass of A, I'll just write it here, is 5 kilograms. And then they gave us VB as well as negative 4 I hat meters per second. And then MB is 6 kilograms. And then we can use the the vectors to get the magnitudes. So the magnitude of VA. Should I write I next to everything, or is
Not necessarily.
Okay.
Now we're talking.
Okay, and that would be square root 9 squared, which is just 12.73 meters per second. And to get the theta, because we're looking at x only, this is only in x, so we don't have to worry about that. However, this one has a x component and a y component, so we have to find that theta for A. And it would just be tan inverse b over a for the vector, or y over x for the vector, which we have is just 9 over 9. So tan inverse of 1, which is 45 degrees. And to get that x component, it's just cosine of this angle here, 45. So VAX, VAX equals VA cosine theta A, and that equals 9 meters per second. Which I realize is kind of, you can just see that from here, but just to show my work here, to show your work more, I guess, yeah. So, and then VBX, since it's only in here, it's -4. Okay, and to get the linear momentum in the x direction, we have ma times VAX plus mb VBX. And so we have 5 kilograms times 9 meters per second plus 6 kilograms times -4 meters per second. And then we can just sum this up, and it sums to 21 kilogram meters per second. Yeah.
Another question.
Yeah.
What happens if the ball is rotating around its center? Will the answer change or will it remain the same?
Okay. The ball rotates across its body. Well, if you're saying it's moving at the same velocity, though, right? Okay. Well, if the velocities are the same and the masses are the same, would the linear momentum be the same? Okay.
Just trying to confuse.
Okay.
All right, so there's two states in this problem. There's the initial state. I'm going to call this, well, this marker is not working anymore. Okay, so I'll call this state 1. It's the same diagram there, but here you have M is 7 kilograms. I'll say MA is 7 kilograms, MB is also 7 kilograms. And it moves to a second state, which isn't really depicted there, but it looks something like this, where the two objects have collided, and now they're moving in different directions. So it's state 2. And I'm going to say this is VA1, VB1, VA2, and VB2. And then so that's the setting of the reference frame. And then just writing everything out, what we have. So okay, so the goal is to find the change in linear momentum from the second state to the first state. So from Atharva's formula earlier, there were two components of linear momentum, but the particles' masses themselves aren't changing. So the first term goes to 0, and we just have that L generally is M A, or I'll just say M X Vx, just for some mass with its respective velocity. And also, we only care about the x component of momentum. So basically what we're looking at is delta L in the x direction, and that's going to be equal to the sum of linear momentums in the second state in the x direction minus the sum. Oh yeah, sorry. Sum of L in the first. So we can just compute this very easily. In the second state, you have, let's see, so yeah. Wait, hold on. Okay, for A, it's 7 times -3 root 2. And I'm going to write the units out a little bit after this. Plus, so this is for A in the second state, and then for B in the second state, it's 7 times 3. Units are going to be kilograms, meters per second. Minus, and then you have 7 times 3 plus 7 times -3 root 2 kilograms, meters per second. And then, sorry, this is delta Lx, and the reference frame isn't changing, so everything is still in this inertial reference frame, and then this all just cancels out because you're subtracting 7 times 3 minus 7 times 3. So the change in linear momentum in the x direction is 0. So momentum is conserved in the x direction.
You now have the next 3 questions.
Okay.
Yeah.
From this?
She had that one.
Huh? Oh, I have another one? All right. I'm not drawing that plane, so just use your imagination. We want to find the angular momentum about the center of mass. So the formula that we receive for that is H, see, angular momentum equals, or we were looking for the magnitude of angular momentum, so I'm just doing magnitude, I, Z, or, okay. Since it's 2D motion, you can assume that this is coming out in the k-hat direction, and everything is going to be scalar because we're just looking at the magnitude. So we're given the moment of inertia about the center of mass to be 275,000 kilograms meters squared. But they wanted n times 10 to the 6 kilograms, which is a gigagram. So 0.275 GG times meters squared. So that's I. And then omega, sorry, is 0.3 radians per second. And very simply, you multiply these two together, and you get 0.0825 gigagrams per meter squared, times meter squared per second, just the same as 0.825 times 10 to the 6th kilograms times meter squared per second. And then, yeah. Yeah. Yeah.
Mine's the same problem here, except I have to find the the magnitude of the sum of all forces. So aerodynamic and then thrust and gravitational and 10 to the 6 newtons acting on the F-16 at time 2 seconds. So they gave us mass as 15,000 kilograms. We know that, so that means we know that mass isn't changing. So we can just say the sum of forces is m times dv dt. So we have the v vector as given there, v naught t cosine theta t I plus v naught t sine theta t j. And we're given theta, we're given omega, we're given v naught, so we can rewrite that v naught, the equation with all those plugged in. So v equals, first the v naught is 273 minus 5t, so 273 minus 5t. Then we have cosine theta, but theta is just omega t. So we have omega t, and that's in the I hat direction. And then we have v naught again, which is just 273 minus 5t, sine theta, which is same omega zt. And so we have the m, so we literally, all we need to do to find the sum of forces is take the derivative and multiply by the mass. So for dv dt, And for that, we would have to do derivative of this. So first part for I, you can just use product rule. So f times the first function, if you call this f and g, f times the derivative of g plus g times the derivative of f. So to write that, we would have 273 minus 5t times the derivative is just negative sine omega zt, but then you also have to take into account chain rule. So we're multiplying by this, omega z. And then that's all in the, or wait, one second, that's the first part. And then plus this function times f. So we have plus cosine omega zt times negative 5. Yep. And that's all in the I hat direction. And then we do the same thing for this part. 273 minus 5t times cosine omega zt times omega z plus g, or the second function, sine omega zt times negative 5. And if we evaluate dv dt at omega equals 0.1 radians per second and t equals 2 seconds, we get negative 10.12 I hat plus 24.8 j hat. And to find the force, we just have to do mass times. Oh, right. Yeah, so this is derivative of velocity. So it's acceleration. So we have it as meters per second squared. Okay, and so it's times dv, it's times the magnitude of dv dt. So, or actually, I'll find the vector first for the force, and then I'll take the magnitude at the end. So multiplying m equals 15,000 kilograms to this, we have negative 151,880 I hat plus 371,736 j hat, and this would be in newtons. And then we will take the magnitude of this. So square root negative 15. And when we do this, you would have it in newtons, but we want it in terms of 10 to the 6th newtons. So I'm just going to preemptively just divide this by 10 to the 6th. And we get this 0.4016 in 10 to the 6 newtons. Is this the right way to show it, or should, yeah, okay. Oh my, yeah, I guess you could do it that way too. All right, yep, that's my question. Oh yeah, this was a bit interesting. So the way I saw it, there was a couple ways to interpret the problem. One is like you could draw out all the forces and the moments. The other way is you could use a formula. So I started with the moment formula is equal to d dt of I omega, I being the center, I being the, let's call this z. and I is being the moment of inertia. So we know that the moment of inertia doesn't change. So we're going to call this I C Z C times d dt of omega. They gave us omega, 0.3 radians per second. So d dt 0.3 radians per second. Since there's no time component to this, derivative with respect to time ends up being 0. So I times 0 is going to equal 0. Sum of moments is 0. Another way you can think of it is that all the forces acting on the plane are acting directly in line to the center mass. So the thrust is going directly from center mass outwards. Gravity is acting on the center mass if we consider this a point particle. And then same with like the aerodynamic forces is acting on that center mass. It's in line with it. So there are actually no moments and any like remainder moments cancel out. Yes?
So let's say the aeroplane mass is distributed non-uniformly such that the center of mass remains the same. What happens to the net force and the net moment acting on acting around the
So did you say the
mass is distributed non-uniformly?
non-uniform? So there's different gravitational vectors. You can basically consolidate like them into like what is it? Infinite different gravitational vectors, and each one of them will have their own force and their moments. If it's not at the center of mass, it might be different. Let's say like you have a lot of mass up here, but most of the mass is here, so that the center of mass stays the same. Then they might the forces will be the same, but the moments might be different.
Forces will be the same and moments might be different.
Yes.
Well, should we go back?
Go back.
Yeah, sure.
Oh yeah.
Yeah.
The person who had number 4, do they want to go next?
We can go back up to number the very first problem.
Sure. Which one was that?
It's 2.2 or 1.2.
Yeah, this one. Right?
There's one more.
Oh,
This problem.
No, it's not.
the one before this.
Yeah.
Yeah. We didn't have anything before this.
Okay. Okay, we have this rigid body, and we have to find the center. Yeah, the center of mass with respect to the distance between the origin and the center of mass of this entire rigid body. So first we find the center of mass of of each one of these bars, and then we add them together. So this vector right here, this is the center of each bar, and this is the mass of each bar, and this is the mass times their center. Adding all of these up together, we get -2, 1.8, -4.7. To get the exact location of the center of mass, we have to divide it by the total mass, which is 9.8, and this gives us this vector. And then the magnitude of this is equal to 0.5526.
What if I change the, let's say I can manufacture a rod such that A has a diameter of 1, B is a square cross-section of 2, and C is a star-shaped cross-section with 3 units, and D is a circle, the cross-section of the rod. What happens to the center of mass?
My initial thought would say it should still be the same.
Why is it?
Yeah, same mass.
No, but center of mass is the position.
But it's the same distribution over the bars.
That's it.
Oh, okay.
The moral of the story is stay with your intuition.
This one.
Right?
Yeah, that one. Okay, for this problem, we have to calculate the angular momentum within the z component about the origin of the set of particles. So basically, we take the cross product of the position with the position of each particle with respect to its own velocity. Then we add those two momentums together. How am I going to do this? Okay. Do I have enough room? I do not have enough room. Okay. And then you have to multiply R cross V times the particle's mass. 2, 0, comma, 0, comma, negative 500. Particle B. And then you add those two together. So you get your final answer as negative 220 kilograms times meter squared over seconds.
I have a problem.
Yes.
So let's say the two objects collide, then they separate, such that now you have the center of mass of these two objects, right? Later on, after they separate, also you have a center of mass of them. Can you tell me what is the change in angular momentum between these two configurations?
Wait, repeat that.
So let's say the body, you have calculated the angular momentum rate of the system here. Let's say they collide, they separate. Now, what is the angular momentum difference between the final configuration and the initial configuration?
There shouldn't be a difference because there's no outside forces. And that's the answer to number 6.
Outside
Forces,
forces or
outside forces are
Yeah, any outside forces or torques.
torques.
Yeah.
It's also yours, right?
Yeah, that was the answer to 6.
I didn't know that. I can bring it. Yeah.
It's the first first rocket problem. It's the next problem. Come on, marker. It died. Okay. That's a nice rocket. I mean, jet. It's fine.
For the chat.
Yeah, I'm not sure of that.
Okay. So for this problem, we had to find the magnitude of the linear momentum. So for that, first we had to find the velocity, and the velocity was given by that equation at the top, v, and the v naught. So at t equals 1 second, the value of v is, yeah, yeah. Okay, and to get the, in my notes I didn't get this exact answer. To get the linear momentum that I just put as Lm, you have to multiply the velocity times its mass. Which gives you this number, 5.659, 76289, 0.2302, 0 kilograms times meters per second. And now we want the magnitude, so we have to take the magnitude of Lm, which is equal to 3840000. But the question asks for it to be in 10 to the 6 kilograms meters per second. So this converts to 3.84 times 10 to the 6 kilograms meters per second. Number 4. Oh.
Yeah, so I think it's the next one. Yeah, this is it. Yeah. Yeah, this one gave me a little bit of trouble, but with some help, I was able to figure it out. So that's our system. It's 2 bars that are welded together. I will draw it just like. Okay. Just assume this is straight. Yeah, okay, I'll just deal with this marker. Okay. Oh my God. Okay. Anyways, so A is 4.0 feet, B is 6.3 feet, and we're asked to find the moment of inertia with respect to the center of mass in slug feet squared. So we have the coordinate system they gave us, x and y. So x goes like this. So it's like that. So we first find the center of mass, because then only we can go from there and get the moment of inertia using parallel axis theorem. And that's the mistake I made earlier. It's not the perpendicular distance. It's the actual distance between the center of mass of the whole thing to the center of mass of each bar. So to find the center of mass, we have the lengths, but we also need the actual mass. So they tell us that each bar weighs 3.1 pound per foot. So to find mass of A is just 3.1 pound per foot times the 4 feet, and that equals 12.4 pounds. And then mass of B is 3.1 pound per foot times 6.3 feet, which is 19.53 pounds. So to find the center of mass in the x, we have the different lengths times the mass. Sum those up, and then you divide by the total mass. So we have 3.1. So if this is our origin right here, 0, I guess 0, 0.
So, you might make the correction later, but remember that it says weighing, it's not mass, weighing 3.1 pounds per feet. Right? So it's the weight, which is a force, not a mass.
Oh, right. So I'll just replace this with WA, WB then? Okay, yeah. Yeah. 'Cause- bro, okay, whatever. Just put this here. Okay.
You have to convert it somewhere, but more precisely, when you're talking of momentum, you have to multiply mass with velocity, not the weight with velocity.
Okay, so the center of mass of the bar would be, for bar B, would be the center over here. So that would be, yeah, right here. So that would be 3.15, but still on the 0. So we're looking at 3.15 as for the distance here, times all the weight centered there, so 19.53. Yep. Plus, we're looking at, since we're looking at the x direction, the A falls under that axis, so we can say 0 from that side, just for the x position. And then divide that by the total mass, 12.4 from here, and then 19.53. And so you get 1.927 feet. Oh yeah, I probably should have labeled my units there, so feet. Yeah. And then we do the same thing, but for the y position. So y. And so for that, since B actually lies on the same y there, we can say that's 0. And then plus the center of mass for A would be here, which is, since this is 4, half of that is 2. So 2 times 12.4, or 2 feet times 12.4 pound. And divide that by the total again. And we get 0.777 feet. So we know our center of mass is 1.927, 0.777. Yeah. And that, if we were to put that here, it would, I guess it would be somewhere like here-ish, I guess. Yeah. And now we're trying to find the moment of inertia. So first, we're using parallel axis theorem. So we have the sum, so that the total moment of inertia would be the sum of the moment of inertia of each bar, but then like on its own, right, from the center of mass. But then we have to add in the distance away from the total center of mass. which is, yeah, so this is part of the sum here. So we'll have mi alpha I squared for the distance. And so we have the, so for, okay, I guess you can use both, but yeah, d. Yeah, alpha actually will get confused with angular acceleration, right? Yeah, that's fine. Okay, so then we have, the moment of inertia of the rod, which I'll write here as 1/12 ml squared. And for the d part, for the first d part, it's just distance formula. So we have, if we're looking at the point 0, 2, with the 1.927.77, it would just be x2 minus x1 squared plus y2 minus y1 squared equals 2.282. And we'll write that here. So we have, so if we're looking at the first part, for bar A, we have 1/12, the mass being 12.4, or weight being 12.4 times L, which is just 4 squared, plus the md squared, we have 12.4 pounds with this distance, 2.282 squared, and we get total 81.12 pound mass feet squared. And that's just for A. And now we'll do the same thing, but with B. So
This is what Atharva suggested is more appropriate, that you convert everything to slugs to start with, though in this case the answers wouldn't matter.
oh, I was going to convert to slugs right at the end.
Right.
Yeah.
Yeah, because slug is a unit of mass and pound in the way it is used here is a unit of force. It's like
That's
pound
true.
Force, right?
Yeah.
So you can't have the moments of inertia in pound force feet square. So the unit would not be right.
Oh, okay. So
Anyway, it's okay. You can go ahead.
Don't the units still work?
It's not pound mass though.
Yeah,
It's pound
yeah.
force.
Yeah, but I'm just saying, like, whenever you add, you're doing like some, like normally it would be a mass times a distance squared plus another mass times a
Yeah,
distance
see,
squared.
for example, even this, it wouldn't no longer be a center of mass, but center of gravity.
Yeah.
So typically, if you use the weights instead of the mass, but just that in this case, the acceleration to gravity is uniform throughout,
Yeah.
so it really didn't matter.
Okay.
So just for precision's sake.
oh, okay. All right.
But you can go ahead with this, but just wanted you to be aware.
Okay, yeah. So for the second part, we have the moment inertia of the B bar plus md squared. So that's just 1/12 ml squared like last time for the bar, but then you add the md squared. The new distance for B is we use the point 3.150. So 3.15 minus 1.927 squared plus 0 minus 0.777 squared. So let's take the square root of that. We have the distance as 1.449 feet. So to plug that in here, we have 1/12, 19.53 pounds times the bar length, which is 6.3 squared, plus 19.53 pound times the distance we just got, 1.449 squared, and we get 105.603 pound mass feet squared. And then we add those to get the total moment of inertia, because the moment of inertias are additive. And then we get 186.724 pound mass feet squared. And to convert this to slug feet squared, one slug is 32.174 pound mass. And then we get that it's 5.80 0.036 slug feet squared. Give me that.
Oh, yeah.
Okay.
So if you take that object,
Yeah.
and you put it in a fluid, right? Like let's say you put it inside water. What happens to the center of mass?
To the center of mass? Okay. Okay. So since the center of mass, and since the center of mass, I guess, doesn't it depend on, wouldn't they have the same, wouldn't each bar have the same center of mass? So,
What's your answer?
so would it be the same?
Okay. What happens to the center of gravity?
I think the center of gravity changes because now since it's in the fluid, you have that buoyant force. Does that do any? Is that not? Okay.
One more
Yeah.
question. Let's say that's being rotated about the center, right? The object there, the perpendicular L-shaped object, is rotated about the center.
Okay.
But
All right.
you have manufactured, there are some imperfections. Okay? So now I have to use a motor to rotate that L-shaped bar. Like initially I calculated some torque that I have to give to the motor such that the L-shaped bar should rotate in a certain angular velocity.
Okay.
Now you have imperfections. What should I make sure such that the torque provided will give the same angular velocity?
Okay. Okay.
Did you get the question?
You're saying what should be provided to know the?
Now you drew L in a weird way, right?
Yeah, that's true. Yeah.
Let's say instead of that, I use this.
Okay. Okay. Yeah. Sure. Yeah.
Now,
So now
should
that-
I make sure such that if I provide a particular torque, this object still rotates at the same angular velocity?
Okay. Sure if I know this angle to this. So the center of mass of this would be different towards that because of the imperfections, right?
Yeah.
So I guess that means the moment of inertia would also be a little different. So the force required to make it move an angular velocity will also, let's say it's this angular velocity, it should be different. And you're asking what I should be provided to know?
So essentially you answered the question. You should make sure that the moment of inertia about that point is same.
Oh, okay, yeah. So, but since it's different, you can't use the same force. So yeah, we would have to know the moment of inertia in order to get that force. Yes. Okay.
It's so nice. Now that I lost the ink on my other pens. Where the
This one's pretty bad still.
okay. So this figure is tilted, so I'm gonna make it straight because simplicity. Let's pretend that this hoop doesn't exist and this is just a straight rod. Because it didn't give us any information about the hoop. Okay, this is bad.
Yeah, okay.
Oh, nice. So we have a rod here. We have this semicircle looking thing. We'll call this bar R. The length is this. From here, this is the radius R. I'm going to call this C, which is the mass of the hemisphere. And I'm going to call this point A. This hemisphere is denoted by D. And I'm going to call this point the origin, O. We have an inertial reference frame. So I, J hat, K hat, and we'll call this I. And that's about the origin. So let's specify here. we have the values r is equal to 0.6 kg, d is equal to 2.5 kg, L is the length 1.3 meters, R is the diameter, radius, sorry, 0.15 meters. Okay, so we have the equations. I, Z, Z, C is equal to sum of I, Z, Z, C, I plus M, I, D, I squared. So we have two parts, the rod and the semicircle. So we know that the moment of inertia of rod, I, Z, Z, C rod, is equal to, about a center mass, by the way, is equal to 1/3 R L squared. I'm just going to plug in the values, plug in the variables that we have. And then we wanted about its, we wanted about the end, so the origin. So we're going to add the mass, which is R. And then D is the distance from the center mass to the origin, which is L/2 squared. And that simplifies to 1/12 RL squared. That was easy enough. Now we want the moment of inertia for the hemisphere. So we want I, Z, Z, C. I'm gonna, what did I call this? I'll call this semicircle, SC. So first we want the moment of inertia for around its own center mass. However, it's a bit tricky to calculate directly, so we have an intermediary step of moment of inertia around point A. To get the moment of inertia around point A, since it's a hemisphere, we pretend that there is a full circle here.
Change 1/3 and 1/12.
Huh? No. I added these together. You square the L/2, that gets you 1/4. 1/3 plus 1/4 is 1/12. I think it's.
I think you interchange 1/3 and 1/12.
Yeah. Sorry. Yeah. My bad. I had it kind of backwards in my notes, so that's why. Accident. The calculation still worked out though. I did not put 1/12 into this. I put 1/3. I made the correct. Yeah. Okay, so for the semicircle, we want it to be over point A. Let's pretend that there is a full.
Remember that the moment of inertia would be minimum about the center of mass. About any other point would be larger than that.
Yes.
So the smallest value is 1/12.
Ah, yes.
So 1/3 is more than that.
Yeah. Okay, so let's do around point A. Pretend we have a full circle. That full circle is going to have a mass 2D. Wow, okay. How did this die out so quickly? And then the moment of inertia for a disk, a solid disk, is going to be 1/2 mass, and this is going to be R squared. That's for the full circle, so I'll just call this C.
Rod is not with superscript C, right? You got it with superscript A. Because you got it at the end of the rod, because you used L/2 square. So just this length and you get to A.
Yeah.
The center of mass.
So I'll actually put O, because it's the same thing, and we want O over O. So we want C here for this circle is going to be 1/2 2dr squared, which is going to be dr squared. However, this is a full circle. We want the semicircle. I, Z, C of the semicircle is equal to be 1/2 dr squared. And this is because the mass is evenly distributed, and it would just basically be half of the full circle. It's distributed in the same way. Okay, so now that we have, no, sorry, this is A, my bad. We have this, and we need to find the moment of inertia for the hemisphere around the center mass. the way we do that is using the parallel axis theorem. I z c s c c is equal to I c z s c a plus m d squared. These are general terms. And we want the distance A to C. So this distance, A to C, is actually going to be 4r over 3 pi. And this is from statics. So if you put that in, if you put all of this in, we get IZCSC is equal to 1/2 dr squared minus the reason why I did minus is because it's going further down, and we want it over O.
It's not that it's further down.
Wait,
it's
sorry.
Towards the CG. Center of mass.
Going towards CG instead of going away from CG.
Whenever you want to go from some other point to the center of mass, you will subtract md squared.
Yes. And then we have, this is d times 4r over 3 pi squared. So now we finally have I, Z, C, S, C. Okay, now we add up these two together and then we use that, never mind. Don't do that yet. We actually want the moment of inertia of the semicircle around point O. We use the parallel axis theorem again, and we get I, Z, Z, O, S, C is equal to 1/2 d r squared minus d 4r 3 pi squared. Sorry. Plus, and then the mass is still the same d. And then we have the distance is going to be L plus that 4r over 3 pi. All squared. And then basically add up everything. So I, Z, Z, C is it going to be that plus 1. Why is the thing moving back? What is it? 1/3 R L squared, which if you plug all the numbers in, you get 5.0049, wow, kilogram meters squared. Yes?
What happens if the whole system is rotating over the x-axis instead of the y-axis? What changes in it? I'm not sure about the answer.
You basically want that rotation. The moment of inertia is different for this, and this one kind of stays the same because if you look at it, it's just a rotation. Actually, wait. Does the moment of inertia stay the same for this as well? I'm trying to imagine it.
If it was a hemisphere, it would be the same. It would stay the same.
Yeah,
It's
because
not here, it's a semicircular disc.
yeah.
It's like a rectangle instead of for the x-axis.
Rectangle instead of.
Let's say the semicircle is the thickness of A.
Okay.
Can we like assume that it's just a long word with that plus r distance? Does it not look like that?
It doesn't, but it could be a reasonable approximation because L is large compared to R. So,
Yeah.
so that's why it will go.
Just because if you take this as your axis of rotation for the moment of inertia, this mass distribution on this axis is different than the mass distribution on this axis. So the moment of inertia for the semicircle disk would actually be different. So the overall moment of inertia would be different.
And that's an important point you brought up. You had to do a subtraction and then an addition, subtraction to get to the center of mass, and then addition again to go away from the center of mass further down. Many people would just think that they can do just with the difference, but that wouldn't work.
Because you square the terms.
Exactly.
So the
that's
square
something to be careful about.
Yeah.
So glad you brought out that point.
I actually did that first.
Yeah.
So I made that mistake first. I found out that that's not the correct answer. And then I realized you have to go towards the center of mass. You can't go from point to point. Okay. That's it for me. Who's next? It just feels this one kind of sucks, but it's doable. If you want to recharge.
Let me just, yeah. Okay.
Yeah, more 25 hours from status.
You could find it in the tables.
Just look up center of mass on the study circle and then read the other question.
Okay, so for this question, the center of mass of the circle is currently, well, should be located at point Q. However, this little circle is cut into it, and now the center of mass has shifted to point C. So we have to find the distance between point Q and point C. So for that, yeah, okay. What do I call this? I just called it D. You have to take, I used this equation, so it was the area of the first circle times its location minus the area of the second circle all over the difference in their areas. Okay. So the area of the first circle is 25.3 squared times pi. Its location, I'm using Q as a center, so its location is going to be 0. Minus the area of the second circle, 4.5 squared times pi, times its location, and this distance is 9.5. Oh, and this little r is 4.5, and this big R is 25.3. Okay. Yeah. So its location is, with respect to like Q, is negative 9.5. Squared pi minus area of the second circle, 4.52 squared pi, and then from here, you get the distance between point Q and point C. .3104. Of course.
Let's say your initial configuration is just a disk thing. Now you have taken the smaller radius out. Now I place it at a different point such that the distance between the D remains the same. It's not at the same point, you still have the code. But now you're placing that circle at a different point such that it's at a distance D from Q. Okay? Did you understand?
Okay, so like you're saying basically like what if this circle was to be up here?
Yeah. So
Then
what happens to the center of mass of the changed configuration? What happens to the moment of initial change with respect to the initial?
okay, the center of mass basically if you were to move this up here, C would be in the same place but flipped, if that makes sense.
I think he's asking like whatever you took out from C, if you place it on top, right?
Yeah.
So if like that mass that you took out from C, if you just place it like on top of the circle at a distance D away.
Oh, just like actually place the other.
Yeah.
Oh,
Wait, so there's no hole anymore?
No,
There is a hole.
there's a hole,
The chunk
and
of
then you
material taken out from there.
and you just put it on top.
Yeah, put it on the top.
You would have to take the center of masses of both of those, and then add them together.
Okay. Yeah. What happens to the moment of initial?
The moment of inertia. It
The
should
initial
it's still
configuration is just the
it
circle,
should
right?
still be the same
Why so?
because if the total overall mass is the same, and it's still a circle.
What is the difference when you place the circle at a distance D and not at a distance D?
Mass
I
distribution
just tell
becomes
the
different.
answer. So yeah, exactly.
Mass distribution becomes different. If you put it at D, it's the exact same like thing that you're subtracting and adding. It's just different. So the moment of inertia around the new center mass stays the same. However, if you like do a different distance, then the mass distribution is like uneven. So depending on if it's less or more than D, you can have a greater moment of inertia or less moment of inertia. Depends.
Okay.
Can you leave the circle?
Got you.
I'll just use a different one. All right, so radius of gyration, everyone's favorite. There's different values. I'm just gonna really quickly, I have to do what she did in the first step. So I'm just gonna do it really quickly with different values. So we have big R, little r, and then I'm just gonna label this distance, call it L. So we have R is 21.5 meters, little r is 4.1 meters, and then D is 8.8 meters. L, we're gonna find out. So from statics, we have that equation that the y position of the centroid, so C, is equal to sum y a over the sum of areas. So we're basically going to treat this hole as like a negative mass in a way, but let's first look at the overall circle. It's going to be its position from Q is 0, and its area is pi big R squared. And then it's a sum, so we add, and then the distance from Q, we're looking at the smaller circle now, from Q to R is D, but in our axis system, which is X, Y, in these directions, it's negative D, so, and it's a negative mass, so it's negative mass, whatever that really means. But negative, we're subtracting the area, and then it's in the negative D direction. So that's the position, and then the area is just pi r squared with the little r. And then the total mass is the big minus the little. And this comes out to 0.33209 meters. So that means that this distance L is 0.33209. I'm going to erase this because I need some space. But also note that the this total area is going to come in handy later. It's 1399.39 meters squared. Okay, so we have that value. And now we're trying to find the radius of gyration. And to do that, you need the moment of inertia. So we have to find the moment of inertia with respect to point C. But this is a cross section, and technically nothing has mass. So we're going to be looking at the area moment of inertia, and then we're going to use that value. So let's first look at the overall one, the big cylinder. So with respect to C of the cylinder is pi over 32 times 2r to the fourth, and then by the parallel axis theorem, it's plus pi r, the area, times its distance, which is L squared. And this, you plug in, so R again, and L, and this comes out to 335,800 meters to the fourth. So that's the area moment of inertia of the big cylinder. And then you do the same with the small one. So whole pi over 32, 2r to the fourth plus, or sorry, this is little r, pi r squared. And then the distance this time isn't just L, it's d plus L, so d plus L squared. That comes out to 4847.98 meters to the fourth. So you can kind of see that this isn't really drawn to scale because this moment of inertia is like way, way larger than this. So this is actually like super tiny. And then the net moment of inertia is going to be, we're going to treat this like a negative mass again. So it's going to be 335,000 meters to the fourth minus 4847.98 meters to the fourth. And that comes out to 330,952 0.18 meters to the fourth. Okay, cool. So we have the net moment of inertia of this object with respect to this point C. And the equation for radius of gyration based on area moment of inertia and total area is, it contains these components. This is the formula where K is the radius of gyration, A is the total area, and this is the net moment, area moment of inertia. So you just get K equals the square root of IZ net C over A. We got A earlier, it's this value. We have the net moment of inertia, it's this value, and so that comes out to be 15.3785 meters. And the units work out because you have meters to the fourth over meters squared, square root, and that just becomes meters. So yeah.
So
Yeah.
will the area moment of inertia and the center of moment of inertia remain the same?
When does this remain the same?
That's the area moment of inertia.
Yeah.
When will the actual moment of inertia and area moment of inertia remain the same? What's the condition that says that?
Interesting. So I don't know. So I don't know exactly the relationship between moment of inertia and area moment of inertia, but
Maybe I think I was talking about 60 over center.
oh, center of mass?
Maybe I made a mistake.
It simplifies to 1/2.
Mhm.
It's the same thing.
Yeah,
1/32.
but you're doing area instead of mass.
Yeah.
Yeah, okay.
It's always
Okay.
the same.
Is it the same?
I don't think it's the same.
Yeah,
If it's
it comes in
uniform
picture
density.
because you have the mass weighting factor. Right? So
That's like
so it's a
distributed.
uniform
Yeah, that's if it's uniform,
density,
just
so then
then it is the same. Okay, that makes sense. Oh, sorry.
Okay, so we have a basic physics 1 problem. We have a ball rolling down a hill. The distance is d, the angle is theta. We have theta is equal to 53 degrees, d is equal to 17.6 meters. Mass is unknown, equals m, and then radius, also unknown, equals to r. However, we shall prove that these two do not matter in the end. So we want the free body diagram. So we have gravitational force, mg, I would call that. We have normal force, and we have frictional force. Because a lot of these forces are acting in the parallel and perpendicular to the slope, I'm going to call the, actually wrong way, x and then y, and then there's the inertial frame of reference. So we have sum of forces in the x direction is equal to m x double dot c, which is equal to mg sine theta minus frictional force. Sum of forces in the y direction is equal to m y double dot c, which is equal to n minus mg cosine theta. However, this term really doesn't matter for our calculations. And then we have sum of moments. About the z-axis, let me put vectors here real quick. This should be a vector as well. Yeah, okay. About the z-axis, about the center mass. I, z, c, theta double dot, yeah. I'll just treat them as scalars because it's easier to break them apart into.
Once you put x and y as subscripts,
Yeah.
scalars because the components.
Yeah, exactly. Okay. So I will actually take these out. Okay. So we have these two. We know that this is equal to FR, which is the FR sine theta. Sine is going to be 90 degrees, or the theta is going to be 90 degrees, so we're just going to simplify this FR. And we can set this equal to IZCC, which is the moment of inertia around the center of mass, is equal to 1/2 m r squared. Take out the r's, we get F is equal to 1/2 m r. And then, oh wait, there we go. No, not 1/2. Actually, this is a, it has its mass concentrated on the outside, so it's actually mr squared theta double dot, and then we equate this to 1/2 r theta double dot. Okay, now we can plug this into this equation. So we get f of x is equal to m r double dot, which is equal to m g sine theta minus m r double dot. The reason why I did this is because mx c double dot is equal to r. Sorry, just x double dot is equal to r theta double dot. So we have this equation.
F still has an m, right?
Sorry?
F is equal to 1/2 r theta double dot.
That's incorrect. That is m. Plug this in, we get this expression right here. So we basically use this equation and solve for theta double dot because we really want theta double dot because it's rolling. So that means there's sufficient friction for it to not slip. Solving for theta double dot, doing some basic algebra, you get g sine theta over 2r. So now using the kinematics equations, we have for rotational motion, we have total theta is equal to theta dot initial times t plus 1/2 theta double dot t squared. Now this goes to 0 because we assume that the ball is at rest. Theta, the change in theta is going to be this d divided by the radius. So you basically have d divided by r is equal to 1/2 theta double dot t squared. Rearranging and solving for t, you get t is equal to square root of 4d g sine over g sine theta, which is equal to 2.9976 seconds. And that's how long it takes for this ball to rotate all the way down to the end of the ramp.
Sorry for the confusion. It shouldn't have been theta because that theta is different from what?
Yeah.
You could call that as beta or something.
Yes. Let's. And this is. Yeah. Okay. Yeah, all of these thetas are going to be different, actually. I just realized. I'm not correcting this. You know what I mean. I got the right answer. Oh, no.
So, what happens to the time if there is no rolling? Can you, in some way, say compare the times between when the cylinder is rolling and when there is no rolling, when there is no friction?
So, you can use the energy equation. This will have both translational and rotational energy, which will take, since that some of the energy is actually going towards that rotational energy, the translational energy is overall being lost. So if you just have translation or if you have less rotation and you have some slip, it'll actually take less time for the ball to roll down. And this is because like the translational velocity is going to be greater if you put more energy into it. And also the moment of inertia is kind of relatively high since the mass is concentrated. So if you just think about it, it'll take longer for it to roll down with a high moment of inertia. So yeah.
Well, speaking of rolling but slipping, or actually just slipping entirely with maximum friction force, actually. So, yeah. I'm just going to draw everything really quick. So, okay, for this problem, we don't actually care about the moment that the friction force generates because we have the information to solve for time without using the moment equation. So I'm gonna draw it as a point particle because if you were to move the friction force up, you would create a couple like in statics. So it would generate a moment, but we don't care about that. So we have the friction force. Actually, let me define the axes. X, Y, negative. And then this is going to be the normal force. This is going to be, we have theta. So this is mg sine theta, positive x direction. And then here you have negative mg cosine theta. And then we've got m is 10 kilograms, mu is 0.17, theta is 51 degrees. Okay, so let's analyze the y direction first because it'll allow us to solve for the normal force. So in the y direction, we have the sum of forces in the y equals, what do we have? We have n and we have negative mg, so n minus mg cosine of theta. There's no net force in this setup y direction, so it's 0, equal to 0, so we get n equals mg cosine theta. Okay, now let's look at the x direction. Sum of forces in the x equals, actually I'm going to write it over here. Mg sine of theta, positive x, minus f. F is also mu n. So if we just substitute in what we have for m, substitute in mu, we get mg sine of theta minus mu mg cosine of theta. And this all equals, we know it's not moving at a constant velocity, so this all equals ma. And you'll notice that we don't actually care about the mass. The mass just cancels out whenever we solve for acceleration. I'll just put it here. So this goes, and this goes. And then you would get A equals g sine of theta minus mu g cosine theta. And if you plug in these values, this comes out to 6.552 meters per second squared. All right. Now we have the acceleration that it's moving at, and we can use some kinematics equations to solve for the time. So all right, just recall A is equal to, and it's a scalar in the x direction, so I'm not using the vector format, but I'll put an x there. 6.552 meters per second squared. All right, so from physics, we have final velocity. And okay, this is technically an inertial reference frame, but we're not changing reference frame, so it's just redundant to write it down. But the final velocity is equal to the initial velocity plus a delta t. Well, we're told that it starts at rest, so its initial velocity is 0. So then we get the final velocity is 6.552 meters per second squared times delta t. And then we use another kinematic equation for position, which is the final position equals the initial position plus v average delta t. Now, the net force is constant, so the average velocity can be defined by just the velocity at the beginning, or velocity at the end minus the velocity at the beginning over 2. So v average equals vf minus vi over 2. Vi is 0, again, like we said. Vf is 6.552 meters per second times delta t. So v average comes out to be 3.2759 meters per second squared times delta t. Okay, plugging that into here, we also know that in our setup coordinate system, it's starting at 0. And then it says that it's displaced along the incline 9 meters. So that's the final position. So 9 meters equals 0 plus v average, 3.2759 meters per second squared times delta t again. So So you get, moving this over, you'll get 2.747. The meters will cancel out. You'll get seconds squared equals delta t squared. So delta t equals 1.655 seconds. Question? Should I erase it? Oh, okay.
You could have saved one step if you use the other equation in physics, d equal to vit plus half.
Yeah,
at squared.
it's just
So
those
directly
two
you
combined,
get your
right?
delta t.
Yeah, yeah.
So the coefficient of friction is such that the friction is not sufficient, right? How can we make sure that the friction is sufficient such that we can get a loading motion?
So the coefficient of friction, since it's sliding down, is the kinetic coefficient of friction. But if you look at the graph of friction versus like force, I don't know if that's the right one, but basically the maximum friction, once it's achieved, if you go higher than that, then it drops down to kinetic friction. So in order to have it rolling with slipping, you need to have that higher kinetic.
No,
Or,
I'm saying how can we change the configuration in such a way that the friction
Oh.
is sufficient to ensure loading motion?
oh. So change the configuration of what, the setup or the values?
I was looking for changing theta.
Oh, okay. So that you would need, I kind of erased some of the useful work for that, but
Yeah, just
It's either a greater normal force or a greater, like a different, like,
theta. I had the equation up there, but
mu.
Different mu or different theta.
different theta, right? So mu n is equal to mg sine theta. So we can reduce the value of sine theta such that mu n will
Yeah,
be
yeah.
So like you can change the surface so it has more friction,
Yeah,
or
that's
you
also
can
good.
decrease
So, like-
the theta so you get more friction.
Yeah, yeah.
So, which is why we discussed in the class, there's one very simple experiment, determine mu,
Mm-hmm.
to change the theta, and then in terms of tan theta, you will essentially get the.
Yeah.
Okay.
Uh,
It was exhausting to ask questions.
That's it, right?
yeah.